Alright, so let's start on Chapter 1. Chapter 1, we're going to be covering just the basics about what oceanography is and a little bit of the history of it. So first off, what is oceanography? Most of you should come up with the answer of it's the study of the oceans and everything within it. Okay, but how is that different from marine biology? Alright, you hear these two terms, usually they're interchangeable. But what is the exact difference? Marine biology, as we know, is generally the study of the marine organisms within the ocean. So, if oceanography is the study of the ocean and the life within it, and marine biology focuses mainly on the life in the ocean, then oceanography is a multidisciplinary field in which encompasses different other fields into one. So, for instance, oceanography not only incorporates the biology of the ocean, but it also incorporates the chemistry, the physics, the astronomy, the geology, and the geography. So you can see these 6 disciplines that would normally be standalone fields all by themselves. Oceanography incorporates all 6 of them. Because when you're talking about the ocean, when you're studying the ocean, you can't just only talk about the biology. You also have to talk about the chemistry, or maybe you have to talk about the physics, right? Because a fish in the ocean isn't just a fish. I mean, it interacts with its environment, and so the chemistry of that interaction is really important. But also too, if we're talking about an opihi, a limpet, there's physical aspects to where it lives on the coastline that need to be taken into consideration. So a lot of these disciplines are interconnected and related. Alright, so the disciplines that we will be looking at are the physical oceanography aspect of it. So the physical oceanography looks at the waves and the wind conditions and how they interact with each other. Chemical oceanography, so we'll be looking at the chemicals in the ocean and how they interact with each other, as well as how they interact with the physical aspect of it, as well as a little bit of the biology aspect, and as well as the geology of the ocean and how they interact with each other. So we won't be spending too much time on biological oceanography, but the geology will be looking at structures on the seafloor. And for instance, how did the Hawaiian Islands come to be? So we will be looking at all of that. Now, if we zoom out, look at an overview of the globe, you can see the 5 ocean basins that we will be looking at. You can see that the Pacific should be the largest, followed by the Atlantic, the Indian, the Antarctic, and the Arctic. Okay. So we talk about oceans, but we've also heard about seas, right? So we have the Mediterranean Sea, we have the Caspian Sea, and the Dead Sea, the Red Sea, all these other bodies of water around the world. Why do they have different names? Well, let's look at this. An ocean is pretty deep, tends to be fairly large in surface area, compared to a sea, which tends to be shallower, smaller in size, and it is also salty like an ocean. Okay, it doesn't have to be surrounded by land, but generally speaking, it will be surrounded by land to some degree. So, for instance, the Great Lakes in the U.S., those are not seas because they're not salty. Even though they are surrounded by land, they are smaller in size compared to an ocean. They lack that salt component. But the Caspian Sea, that's depicted here, as well as the Dead Sea and the Red Sea, they are salty, they are smaller, and they are shallower than majority of the oceans. Okay, but why do I have an image of the Arctic Ocean over here? Is it just to depict what an ocean is compared to a sea? Let's look at this. Should we actually be calling the Arctic Ocean an Arctic Sea, perhaps? So if we look at these pie charts, you can see that the ocean takes up about 70% of the land of the Earth's surface, whereas land only takes up a little less than 30%. Okay, so majority of our Earth is water, and when you divide up the water portion of that pie into the different ocean basins, you can see that Pacific takes up the most space, and it takes up about 50% of the surface area of that ocean portion. Okay, it's followed by the Atlantic Ocean, then the Indian Ocean, and then they don't have Antarctic on here because it's kind of a special case. But when you look at the Arctic, you can see it's only about 3% of the surface area on Earth. That's a fraction of what the other three are. Okay, so let's look at the depth now. If we look at the average depths of these ocean basins, you can see that the Pacific is just under 4,000 meters deep on average, and then you can see the Antarctic follows the Pacific, and then the Indian is next. And when you look at the average depth of the Arctic, you can see that the Arctic is a fraction of the other three at just over 1,000 meters. Okay, so if you go back and you look at the definition of what a sea is shallow, and it's smaller, and it's salty. So all three of those technically characterizes the Arctic Ocean. So technically speaking, the Arctic Ocean should actually be an Arctic Sea, but just because of naming conventions back in the day, it became an ocean. So we have the 5 ocean basins. Now let's compare some average depths between the ocean and the land, as well as some features. So the average depth of the ocean compared to the average height on land is drastically different. So the average depth is about just over 3,500 meters versus just over 800 meters on land. So that's a big difference, right? And then if we look at the deepest part of the ocean, which is the Marianas Trench at over 11,000 meters, and if we look at the tallest feature on land, that's Mount Everest at 8,000, or just under 9,000 meters, you can see there's a pretty significant difference there as well too. So the point being, there's a lot that we haven't discovered in the ocean because there's so much more ocean to look at compared to land, and there's a lot of it that we still can't reach. Okay, we have been down to the bottom of the Marianas Trench, but it is a very difficult place to get to, and it's not some place that you can stay for very long. So these trips down to the bottom of the ocean do take some time, and so therefore we have not explored as much of the bottom of the ocean as we have been able to explore on land. So let's look at this. I told you that the tallest feature on land is Mount Everest. Do you guys all agree with that? Because I don't agree with that. Let's look at the Hawaiian Islands here. So Hawaiian Islands were created by a hotspot, and that hotspot creates mountains, right? Well, it creates islands, and on those islands are volcanoes, and basically volcanoes are just large mountains that spew out lava. And on the Big Island, we have a mountain known as Mauna Kea. Now, when you measure it from the base to the peak, that height is actually just over 10,000 meters. But when we measure Mount Everest, we measure it from the base to the peak, and that gets you just under 9,000 meters. But its base is at sea level. Now, when we measure Mauna Kea at sea level, it only comes out to just over 4,000 meters. Because when you measure Mauna Kea from sea level, you're only measuring I would say just under half of the mountain. The rest of the mountain is technically underwater. So when you measure from the base, you're actually measuring from the bottom of the ocean. So that's why, technically speaking, Mauna Kea should be the tallest land feature. But because it's in the middle of the ocean, it is not. Mount Everest is technically the tallest. Okay. So feel free to click on the video link and take a look at it. But this is just a short summary video of James Cameron going down to the bottom of the Marianas Trench. The deepest part of the Marianas Trench is known as the Challenger Deep, and that's at about 11,000 meters deep. And when we superimpose Mount Everest into the trench, you can see that it's completely engulfed by the trench itself. Like, no part of Mount Everest pops up above the water surface. That is how deep the Marianas Trench is, and that is how much we don't know about what lives in the trench. Pressures down at the deep are immense, and so if you guys are watching that video, you can see that submersible that he goes down in. That submersible has walls that are very, very thick to accommodate for that increased pressure. We will learn more about that pressure when we get to chapter 5 and we talk about the physics aspect of the ocean. Now let's talk about some navigation, some early navigation, and where oceanography actually started. So just a little bit of history and some background knowledge of oceanography. We're not going to go into too much detail about this. So if you are interested in going into more detail, we can do that outside of the lecture. Okay, so pretty much the first people to do any sort of ocean navigation were the Phoenicians in the Mediterranean Sea. They would travel around the Mediterranean and generally would stay pretty close to the coastline because they didn't have any maps like we do today. They didn't use any fancy gadgets such as GPS or compasses. So everything was done by sight. So they had to make sure that they knew where they were going, and they had to make sure that they weren't going to run aground. So they had to make sure that the coastline was somewhere where they could see. They even ventured out into the Atlantic Ocean and traveled north up to England. Well, it wasn't England at the time, but England now. And you can see they did follow the coastline pretty closely to make sure that they didn't get lost and they didn't go adrift. All right. But they were pretty much the first navigators in the Mediterranean at that time. And they pretty much opened up new trade routes because at that time, the only trade routes were by walking on land, right? So now they opened up a different option for people to do. Next, let's go to the Pacific, and you've got your Polynesians, right? And they are, well, not only the Polynesians, but you got the Pacific Islanders who, it's theorized they started in the Philippines, and they made their way across the Pacific through Micronesia, through Melanesia, and then all throughout the Pacific, the Polynesia Triangle. And they would use a number of different methods to navigate the different islands, right? The Pacific Ocean is the largest, keep in mind. So these particular routes, they traveled the farthest. So one particular method that these Pacific Islanders used to travel around the Pacific Ocean, the main one that you guys should know about are the stars. So when they would travel at night, they would look at where the position of the different stars were, and they would look to see, okay, if the North Star is on my left-hand side, then I know that north is over there, so right behind me should be south. So they would be able to get their bearings depending on where these stars and where the different constellations were at in the night sky. But while they were traveling during the daytime, They didn't have the advantage of the stars to navigate. So they would use something known as a shell map, a Polynesian shell map. This shell map consisted of shells and sticks. Now the sticks represented currents and the ocean direction, and so and then the shells would represent islands. And so if you see a curved stick around an island, that just meant that the current around that island curved and swung around the island. So whoever was navigating the vessel knew that, okay, well, I can't just beeline straight for the island. I've actually got to swing into the island or whatnot. And keep in mind, these shell maps could only depict a certain area of the ocean. And so if you were doing very long distance traveling, you would need to have multiple shell maps in order to know where to go. And a lot of the information from the shell map needed to be passed down orally, because as you can see, it's only sticks and shells. So, and if the shells were representing islands, well, how did you know which island was what? So that information was definitely passed down orally, and you needed to remember all of that information before you headed out. So it was interesting. All right, so now let's zoom to the Atlantic Ocean, the northern Atlantic, and you can see the Vikings did a little bit of traveling in the North Atlantic, and up in the North Atlantic, it's definitely a lot colder, a lot more stormier than in the Pacific. And so the way that the Vikings would get around would be using the sunstone, which is depicted in the bottom right-hand corner. Now, this clear-looking crystal stone, when you point it at the sun, it creates a small little black dot in the middle of that stone. The sun rays, when it hits it, it refracts in the stone itself, creating this small little black dot. And so the navigator on these vessels, they could just stand at the front of the boat, hold up the stone, pan it around a little bit, and find out where the sun was at. And from there, they can figure out their directions. Because if you know where the sun is going to, if it's rising or if it's setting, then then you can determine what direction you're heading in. So that's how they got around. But definitely they would use the coastline. They would follow the coastlines when they could, just to make sure that they knew where they were going. Then a little bit later, you've got your Columbus and Magellan voyages. And Columbus was famous for going to the New World, right? And so he discovered the Americas, so to say, or rediscovered, I should say. And then Magellan, he went all around the globe, and was one of the first to do so. Okay. At this point, though, they definitely did have maps. These maps, though, were hand drawn, so there were some inaccuracies associated with these maps. The coastlines were not always where they should have been, or maybe there was some extra indentations or bumps in them, or maybe there was a few extra islands, Maybe somebody miscounted how many islands were in that group. So for the most part, you got a general idea of where you were going, but it is definitely not as accurate as the maps that we have today. Then we have Cook in the 1700s. He sailed around the world twice. He was also credited with being the first European to set foot on Hawaii. He did that in his third voyage around the world. And you can see he did a lot of traveling, especially on that second one. He went all over the place and looked at all different sorts of things. And then, so where did oceanography begin? So those are just some of the key voyages up until this point, but oceanography really didn't start until the 1800s, when a dude named Edward Forbes decided he was going to travel around the Mediterranean. He was going to take sediment samples from the bottom of the Mediterranean. And when he did that, he'd let his anchor down, pull it up, he'd take a look at what was in the sediment, and he determined that below 550 meters there was no life, because whenever he would throw his anchor down in the deeper parts of the Mediterranean, it would come up with nothing. It would just come up with rocks, sand, maybe some sediment. But he didn't see any clams, he didn't see any crabs, he didn't see any sort of life. He saw those on the samples that were shallower than 550 meters, but nothing that was deeper. So because of this, he came up with the azoic theory. Now remember, theory needs to be tested multiple times by many different people. Okay, so now a little bit later in the 1800s, you have Charles Wyville Thomson, and he made it his mission to disprove the azoic theory. He didn't believe that there was a certain depth at which no life existed, and he thought that there had to be life found throughout the ocean, even at the bottom of the sea floor. So on his Challenger voyage that he was the captain of, he made it a mission to try to find evidence. And when they got into the Pacific Ocean and found the Marianas Trench, they discovered life deeper than 550 meters. So you can see that he was very ecstatic, because then he was essentially the person that disproved the azoic theory and found that life can live deeper than 550 meters. Alexander von Humboldt, he also was doing a lot of work at around the same time, and he gathered a lot of plant and animal species on his voyages. And he is famous for collecting meteorological data. He was one of the first explorers to do so, and he basically is a forefather of meteorology. He, on his voyages, would collect information about how sunny it was, how rainy, or what the weather conditions were like, in addition to his plant and animal species. And lastly, there is Darwin. So Darwin is famous for writing his book on the origin of species, which detailed his theory of evolution. And he did this by looking at finches on the Galapagos Islands. So these are islands off of the coast of South America, over by Peru and Ecuador. And these islands are very special because each island has a group of finches, a population of finches, and depending on the island, each finch developed a different type of beak size, morphology, to accommodate for the resources found on that island. So let's just say one island, the food resource that was most common was a very soft seed, like say a grass seed or whatever that doesn't have a shell around it. That finch would develop a beak that wasn't very large and didn't need to be very powerful to break open, say, a very large shell like a walnut or something, because they didn't have to. And then let's just say on a different island, the only food resource that the finches could take advantage of were these really hard shelled walnuts, let's just say. And these finches, they needed to evolve a beak so that they could smash open that shell that was powerful enough to smash open that shell so that they could get to the food resource. So each island had a population of finches that developed very different morphologies from each other, even though the islands are very close to each other. It was solely dependent upon the food resource that was there. And so this is how he kind of came up with his theory of evolution. He's also credited with coming up with the theory of coral reef formation. So along his travels, he noticed that there were certain islands that had coral reefs around them, much like here in Hawaii. But then he also saw just like random rings of coral reefs out in the middle of the ocean. And so, for instance, Midway Atoll in the northwestern Hawaiian Islands, that's a very good example of a coral reef that has turned into an atoll. And so he came up with the theory that coral reefs, they'll go from being surrounded by or surrounding an island to then the island sinking at some point, and the coral reef is left behind. And so you'll see where the island used to be at. And then lastly, he also observed this natural phenomenon depicted by this octopus here. So this octopus is changing its skin color to match the surrounding vegetation so that he can camouflage himself. This is what's known as cryptic coloration. And we won't learn too much about this in this course, but if you take marine biology, we'll learn more about it. But essentially, if you can see, you can only really see his eyes and maybe a little bit more, but he's pretty well hidden within that vegetation. Another phenomenon that's going on in this photo right here is on the photo on the right hand side, that octopus, that coloration on his skin, that's like a warning coloration. So he's warning whoever's taking this photo to go away because he doesn't want his photo taken, essentially. So, yeah. So this is it for chapter 1. There's a lot more information in the textbook than what I've presented here. But for the exam purposes, please just focus on what I have here in the lecture slides and supplement with what is in the textbook. Anything else, any other information in the chapter 1, it would be extra and just for your knowledge. All right, so let's go on to the scientific method next.